Okay. So thank you to everyone for joining us today for our virtual Linux Foundation Decentralized Trust meetup. Today we are talking about the Lockness project. If you are joining us on Zoom, we welcome your comments, questions, suggestions. Please feel free to type in the Zoom chat. That's probably the best way to share, or use the raise hand feature. If you're watching on the live stream or the recording, you'll still have an opportunity to ask your questions. You know, the Lockness is one of the projects we host here, so you're always welcome to get involved in the community. Again, if you're not watching this live or if you're not part of the Zoom call, you can still engage with the project. You can join on take a look at the Lockness GitHub repo or the Lockness Discord channel, and we'll provide those links in the YouTube description. And also, as a reminder, we run our events under our code of conduct. If we just ask that people be respectful, if you want to see more of the details, feel free to check out that link there. And with that, I'm going to hand it over to you, Dennis. So here, I'm going to stop sharing my screen, and you can take it away.
Hey everyone. So welcome to Lockness. I'm Noah. I'm CTO of DFNS, and I've got Dennis right next to me, our lead MPC engineer. We're going to talk about Lockness today. We've been a part of this project for quite a while, and we really love MPC. It's a pretty core foundational part of our company, and have been a part of this open source for quite a while. So happy to have everyone here and give an update. So what is Lockness? This is a production-ready key management solution. It is what we use internally for our MPC infrastructure. We support threshold ECDSA, Schnorr, EdDSA, and ECDH. More coming. And the core of the project is just an ecosystem for developing multi-party computational algorithms. So it's a really cool setup. We want to get more people involved and able to use it in building more protocols. And then Defense, as a company, we're a wallet as a service provider. So we secure MPC keys and provide wallet services. That's the core of our platform. We definitely love being part of the foundation here. Supporting Lockness and building more into it. So with that, I'm going to turn it over to Dennis.
Thank you, Noah. I'm turning the settings. Should be good. So I will start with a quick introduction to threshold cryptography. Before going to threshold cryptography, I will start by regular cryptography, in which we have a single key, which is managed by someone, a user, a company, entity. And in this architecture is the regular architecture without threshold, and key can manage the wallets on the blockchain. It can manage the CI certificates. It's a really sensitive piece of information. If it gets leaked, if it's hacked, if it's non-operational, if it's not available, there are losses. Losses are huge. So usually how we work with key, we have some operation. It could be sign, it could be decrypt, some asymmetric operation. We do this operation with the whole key. We use sign to produce signature. We use decrypt to decrypt the message. And in this case, the key is single point of failure because the attacker can get access to the key. And that's all it gets to steal the funds, to sign unapproved certificates, to infiltrate the infrastructure. And if the key is lost, we can't access funds on the wallet, so we can't keep up with the infrastructure changes. So this is where comes the threshold cryptography, in which the key is split into several key shares among several entities in some T out of n scheme. On the slide, there is 3 out of 5, in which any 3 parties holding the share can engage into the interactive protocol execution, and they will perform the operation like signing. In this scheme, it tolerates up to T-1 corruptions. Like we could have T-1 servers or entities corrupted, controlled by adversary, and they gain no information about the private key. They ultimately need to corrupt T servers or entities in order to extract information about private key. How it can be used. For instance, our case, it can be used for multi-cloud deployment. We can have multi-cloud, multi-region deployment in which a single key share deployed in one region, one cloud. So if one of the clouds mysteriously go away for some geopolitical reason, there is still continuity. We can continue to keep up with operations, even if the server is hacked into somehow. Hacker doesn't gain any knowledge about the private key, and we can change the T and end parameters to get better control of our security model, how we manage risk, how we estimate the risk of one server going away or being hacked into, etc. But this is not the limit for the applications of threshold cryptography. We could imagine many use cases. For instance, the code signing. We could distribute the key among several engineers in the company, and they will, like 3 of them can sign binary to be distributed to the with software upgrades. And even if 2 of them go to vacations, the operations stay intact normally. The 3 remaining engineers can continue signing. And there are many other use cases, just a great framework for defining better security policies, for defining better security model. So there are many good things about threshold cryptography, but what are the catch? What is the catch? Threshold protocols are complicated. While regular cryptography could be expressed like 5 lines of code sometimes, the threshold cryptography, it's academic publication paper that has to be peer-reviewed, which consists of many operations in in several communication rounds, and that is difficult to review, audit, difficult to implement, and most importantly, it's difficult to implement from scratch. If you just start a new Rust project and try to implement a threshold protocol, you will run into a lot of issues, mostly related to the communications model. The way the MPC protocols are structured in rounds, it's not really native to the many languages, like if you start a new project from scratch. And given that it's difficult to develop, maintain, and audit, it's difficult to trust to the threshold protocols. So that's where the Lockness comes in. We have designed our ecosystem. We have built our ecosystem for MPC protocols, so we can implement. So we can streamline the implementation, the development. We can make the code clearer and easier to review. So the actual protocols implementation that we have, you can open the academic paper, you can open the implementation, and you can match those quite easily. You can match that this line corresponds to this line in the code. And we have made a lot of efforts into designing our ecosystem libraries, API that we expose to be secure by design, secure focused, so not to leak any sensitive information, not to allow any accidental misuse of the libraries that can bring to some dangerous outcomes. So this is what does Lockness, and our main goal is to bring trust to the MPC. We have we have 3 protocols, high-level protocols in our in the Lockness project. We have CGGMP, that is a threshold TCDSA protocol that can be used like anywhere CDSA is used, but most importantly, Bitcoin, most of the blockchains with it, like all the CA signing, everything. We also provided, we also built a threshold Schnorr EDDSA. The library is, we call it Givre. It's a Frost implementation. Frost is a standardized threshold Schnorr EDDSA. It's a nice protocol that can, from, I don't remember from what year, but it's also supported by Bitcoin now, the Schnorr signatures, and our library is Bitcoin native. It exposes specifically built cipher suite that is not available in the Frost standard, but we have built it that is compatible with the Bitcoin. And we also have developed a threshold Diffie-Hellman, which have some niche use cases for establishing trust over network when you have to split your private key in several pieces. And we have many other protocols coming. Most importantly, we have coordinated MPC is our, like all the MPC protocols are communicative, interactive by nature. So parties need to communicate with each other. And on how you communicate with each other depends the whole security of the system. Like if your delivery layer is not good enough, then then the security of the whole system is compromised. We're also working on threshold MLDSA. MLDSA is a post-quantum signing scheme approved by NIST. So there is a lot of research recently that looks into how we can thresholdize the scheme. This is the scheme that is the most thresholdizable among others. The rest of them are very difficult to thresholdize. And we also consider if we want to open source Q25, it's our super fast threshold TCDSA that we actually use in production. We have submitted it to the NIST, and well, Q25 is patented, but we consider if we want to contribute it to the open source. And we have many other libraries in the ecosystem that actually help to build MPC protocols. Like MPC protocol alone, as I said, you can't just write from scratch the protocol. And we built reusable modular blocks that you can use to build your own MPC protocol or other crypto system. They are not necessarily MPC specific. We will actually go through them in the slides. I will give a quick introduction in some of the libraries that we have, starting with the Givre, with our threshold Schnorr. But all the libraries that are threshold protocols, they expose similar APIs. So the code examples that I will provide, they will be similar in CGMP or in TCDH. So the libraries are for doing the threshold protocols for all the reasons I just described, why a threshold cryptography is important. And I will demonstrate that our libraries provide simple, easy-to-use API, that they are abstracted from networking, and that they are async native. So if you want to run our threshold protocol, the first thing that you need to define is how parties will communicate with each other. And to do this, we use where is the pen? Laser pen. We use the classical asynchronous primitives, futures and sync, stream and sync from the futures library. They are like not specific to us. It's just classical asynchronous primitives, and you just rope them to our library, and then parties can communicate with each other. But before you start the protocol, most of the protocols, they require execution ID. It's not specific to our library. It's more specific to the protocols themselves, academic papers that publish them. They require that at the execution of the protocol, there is a unique nonce that is assumed to never repeat. Like you start the protocol, all the parties have the same nonce, and this nonce never repeats in any other execution. If it does, the security is affected. And then you can straight run the first MPC protocol to generate a key. Key generation is a protocol that allows parties to generate the key in the way that the private key that they co-share is never reconstructed in any single point. Like every party only learns the key share and the public key. They don't learn anything else. And after you generated the key, you can run the signing, the signature generation, the signing protocol. You can see it's like it's just invocation of the function. You provide the same party that defines how you do the networking. You provide the source of randomness, and here you provide the index of the party, like from 0 to n-1. The key share that is used for signing, the indexes of other parties to match which party corresponds to which party that was on the key generation, and the actual message to sign. So it's one function, and the whole complexity of threshold protocol is abstracted, which is not which should not be taken for granted, because many threshold protocols implementations, they who tried to implement where researchers try to implement the protocol from scratch, they have very complex patterns like state machines, where you have to construct the state machine physically, like manually retrieve the messages. When they receive messages, you have to give to the protocol, and you have to drive the execution, like write a lot of codes to drive the execution in the end, which gives a bad user experience, which difficult to audit the code itself. But we were working hard to solve this problem, and we come up with this approach. Behind all these libraries, we have, behind all the threshold protocols, we have many other libraries. The first that I will present is generic EC. It's a library that we use for all the elliptic curve arithmetics. It is interesting for you to use the generic EC generically if you implement any cryptographic protocol based on elliptic curves. It's not MPC specific, or like many protocols, cryptographic protocols use EC. And we designed the library to have unified API for all curves. So you write the code once, and then you can plug in any curve. And the API is designed to be safe, so that you can't, for instance, multiply point from one curve on the scalar from another curve, which will just produce a compilation error. We have also made many other security decisions, like erasing private keys from memory, preventing small group attacks. This is one of the core libraries in EC infrastructure, in cryptography. So it had to be well done, and it was well done. So also it non-std and WebAssembly friendly, so it can be used anywhere. You can use it in embedded devices. And I will give you an example what it looks like to use this library. So on the left, we have We have a cryptographic protocol. It's Schnorr's signing. And on the right, we have the implementation of the same protocol, but in Rust using the generic EC library. You can see that it's a one-to-one match. In the first line, we generate a scalar. It's standard notation in the cryptography. Then we just do the same operation in the code. We multiply the generated scalar at the generator. So here we multiply the scalar at the generator. Then we produce a scalar by hashing. So this one-to-one match. And this is what I'm proud of, because you don't need, there is no noise of using the library. It's just as ergonomic as possible. And here you have not, you might have noticed that this code uses the SIG P256 K1 curve, and this code will only work with this curve. But it is not difficult at all to change this code to be generic for any curve possible. You just, well, this is all the changes that we need. We change 4 places, and now the function, the realizing function, works with any curve possible. Yeah. So if you need to work with EC arithmetics, why not use this library? We also have udigest library. It's an ambiguous hashing of structured data. When you need it, you need it when you have to hash data and the data is structured. Usually hash functions, well, not usually, hash functions, they take a byte string as an input. But if you want to hash like a list of byte strings, the hash functions do not support it. And the question is, like, if you have structured data, like here on the slide, where we have multiple fields, images is a list of byte strings, how do you hash it? And when engineers face this challenge in a rush, they might not realize that this is a whole new cryptographic problem, that you have to properly encode the structure into the byte string. They might just concatenate all the data in the structure. In the code, it will look like this. And already just concatenation of the data, it's already like 6, 7, 8 lines of the code. And it's even in this code, you can mess it up. But this code is not secure at all, because you can find, well, we will refer to the article why it's not secure. But in short, you can construct several posts that when concatenated will look like one byte string, but they are actually different instances of the posts with different values. And if you think that it's rare to do this mistake, it's actually found, it's very popular mistake in threshold protocol implementation, smart contracts, key proofs. You can find the links in the blog post. And all you need to do to make the hashing secure is to use the library that we have developed. You just add this line to make the structure digestible in an unambiguous way, and then the hashing is just one line of code. Yeah, so this library has 0 boilerplate. You just use the macros. It's flexible. It works with any hashing function. From digest ecosystem. It also supports. You could plug into any hash function. We are not limited to the digest. And the secure by design, we have a formal encoding specification and everything. The next library that I will present is round-based. It is our core library that we use for implementing threshold protocols. Threshold protocols, well, generally MPC protocols with fixed amount of rounds. Why would you use it? Because MPC from scratch is a pain, how I already mentioned. And it is non-steady WebAssembly friendly. It uses async feature of the Rust. You have seen in previous slides how it's easy to use Givre. So you can, so this is actually the reason why it's easy to use, because we have this library, this framework for developing MPC protocols. And just to give a quick example how you implement the MPC protocol, here is the simplest MPC protocol I could think of. It is actually in our repository in examples, so you can find it. So in this example, n parties generate a random byte string. How they do this? They generate a random, each party generates a random string of 32 bytes. Then they hash their randomness, they broadcast it. So all parties receive the commitments, what we call to the randomness. After we received all the commitments from all the parties, we send the local randomness. So this is called commitment and decommitment in the cryptography. Because after we have sent commitment, we cannot change our randomness. We cannot commit to one string and open another byte string, because other parties will detect this. And in this case, the output will be, well, we will parties verify that all other parties honestly opened the committed values. And if everything is good, we just output the XOR of all byte strings. And if protocol terminates, then the byte string cannot be manipulated by adversary if there is at least one honest party in the protocol. Though there are some problems with this protocol, like adversary could abort the protocol. They can observe the output of the protocol and abort it if they don't want this protocol to terminate. Well, that's not the point. We will just see how easy or difficult it is to implement the protocol. So we will start by defining the messages. The protocol sends messages, the commitment, and the decommitment messages. So we define the messages, and we start we start implementing our protocol. This is a function that we will use. It's async. You take the MPC thing, which allows you to do the message routing, the networking. It abstracts with the networking. And the protocol implementation starts by defining the rounds of the protocol. We define all the rounds that we have, and then we just go straight to the implementation. So it is, I claim that it's as readable as possible, because the first step, we generate randomness. Here, we generate randomness. Easy. We hash the randomness and we send to other parties. That's what we do. We receive all the hashed messages from other parties. We send the randomness to all other parties. We receive the message, and the final step is as long as the previous part, but it's just how much code it takes to verify that all committed messages, that all hashes correspond to the actual randomness that we received. And this party, it actually has sort of identifiable abort, because if one party revealed another byte string that does not correspond to what have been committed, then we will detect it and we will say that this party has cheated, and we will even say the message IDs in which can be used to verify that this party has cheated. And then we just terminate the protocol if there is no abort detected. And you can find this same protocol on the link. And we have the whole ecosystem. I just presented a few libraries that we have. We have many more. I just want to leave some time so we could have some discussions, questions. What is also missing in our ecosystem and what we would like to have? First of all, we have the mentorship program to which we submitted the advanced key management protocols like key refresh, key repair, key reshare. And we submitted there the DKLS protocol for threshold ECDSA. But we also would like to have threshold BLS. We would like to have the different. The last point is our pain point, because we don't have any open source networking implementation for the MPC parties. The reason is that any networking is very, very use case specific. Like while threshold protocol is general purpose, you can do the CI signing, the blockchain management with the threshold protocol. But the networking really depends on your deployment. And here on the slide, I provide some examples, and there are like many examples how what choice of delivery implementations you could have. And what we use in defense is really specific to defense. But it's good to have, it could be good to have some delivery implementations that try to be generic as much as possible, just for people to be able to try out the MPC protocols. Well, we are looking to the contributions to our existing libraries. We have posted some issues, some help wanted. We have mentioned, we have tagged some issues as help wanted as a good first issue. I'm not sure if there are any left, because there are, as we announced the mentorship program, there are many people who came to our libraries and try to contribute, and we don't keep up with all the new contributions that we have. But in general, there could be some improvements. So don't hesitate to reach out to us in Discord, in GitHub issues. We're also looking for the other companies. If other companies are doing their MPC and they are doing on round-based framework, we would love to have them in our ecosystem. We are part of LFDT, which makes the Lockness competitor-friendly environment. We could also imagine have our competitor to join the Lockness, and we would collaborate on the protocols for the good of everyone. Yep, that's it for my slides. I'm happy to take questions, any community discussions, or any other inquiries. So I remember that David mentioned there is a chat. I'm going to the chat. There is no question in the chat. Cool.
So a question just popped up. It's I was thinking of a use case where there are a few NFT artists and they use it to sign their art.
Was distracted at water. The NFT artists use the threshold protocol to sign their art, like collaboration. Yeah, it's a good idea. Like I had more practical use case in my mind where a board in the company, they use threshold cryptography to sign documents, like decision to invest money into this. And the NFT artists could also use this. As far as I know, there are some blockchains who use threshold cryptography for a consensus protocol to approve that the consensus was reached, and NFT artists also could use it.
I'm trying to think, because we work with quite a few NFT companies. We may have had some that have been interested in not just signing their art, but like embedding like cryptographic values into it as well, like for the owner of the art as well. So there's a lot of like interesting use cases that you can kind of think of. when you start expanding, outwards.
And I just checked the live streams. Excuse me. People are viewing it there, but I don't see any questions coming in on either LinkedIn or YouTube right now.
Okay. Well, I also redirect there. I announced in the Discord if for the contributors to come, and if there are any contributors who want to discuss PRs, we could also do this. So don't hesitate before we drop off.
Great. Yeah, last call for any questions. Okay, looks like there aren't right now, but again, oh wait. There is somebody who just asked about traits.
And traits, when is it good to use a trait? That's a generic Rust question. There are definitely sometimes traits are abused. And I have seen this in practice, but it's just a feeling that I just look at the code and I see that it's not necessary. It's difficult to put into words right now. Yeah, the profiler XT. In this case, I am. So there is in this specific contribution, in this specific case, we could we have a function that wraps the MPC engine, and we can just use the round-based what it's called, what they call the module. But okay, we just can use this function, or alternatively, yes, there is a that seems to be easier way to call these functions by using this trait, but then you have to introduce this trait into the scope. So you have to use this use statement to introduce the trait into the scope, and then you have a shorter way of wrapping the MPC engine. But this takes 2 lines of code, while that's a longer line. It's not that long, and it takes only 1 line. And I don't think that there is any ergonomics in this solution, because I don't think in one file we will ever do the wrapping twice. Like at most we call one file at most calls once the TSS protocol. So there is no saving in here. Saving would be if we envision that in the same file, source file, we call this function multiple times. And in this case, yes. In this case, it could be ergonomic. But for Profiler XT, I didn't see how it's ergonomic. You're welcome.
Wait, we do have a question from YouTube. Let me copy it over to Zoom chat. Sorry, just 1 second. There we go. Sorry, it wasn't wanting to paste.
Are they in your learning curve to understand the repo like I'm looking to contribute by text tags is very new for me now. What will you suggest? One must know who want to contribute to the repo. Learning curve, understanding the repo. That is true that we don't have, well, we do have a lot of documentation in the crates. So if you open, there is extensive documentation how to use the threshold protocols, the udigest, the macro is heavily documented following the example of cert, for instance. So there are use cases that are shown. But learning curve, I guess, not just also probably learning curve of learning the threshold protocols and the cryptography in general. In this case, this complicates things, yes. But well, if you're not scared to start, the threshold protocol are defined by the paper, and if you look at the paper and the implementation, you will see, you will start to understand this language. The paper are written in certain language, like the programming language, but it's closer to human language. And after reading thorough reading of the paper, you will start to understand it. But yeah, you may hit some learning curve peaks in the process. And we also would like eventually to have some book into how to use our libraries with even more extensive documentation. But this is not for short term. But eventually, we would like to have this. Hope this answers the questions.
Great. Yeah, thanks for those questions. Okay, last call for any more questions. I'll take another look at the live streams. Okay, I don't see any other questions for now. But as Dennis was saying, if you have other questions after, taking a look at the code or rewatching the video, or if you're looking at the recording, do feel free to join on the Discord channels and ask your questions there. So this is not your only opportunity to ask questions about Lockness. So thank you everyone for joining today. And if there aren't any other further questions, I think we are done for today. So thanks everyone.
Thanks, David.
Thanks, everyone.
All right, bye.